All right, let's go ahead and get started. So like I said last time, basically this is kind of going to be driven by you. So whatever things you all want to talk about before the test on Monday, it's fair game. So what should we go over? Go ahead.
Where the integral of the natural log of like AX of B.
Okay, so you have a specific one, or do you want me to just?
This one is 9x plus 1, but I don't think it really matters.
So you're looking at something like this?
Yeah.
Okay. All right. So of the techniques we've talked about, what does that most fit? If we try U substitution, what's your U going to be? 9x plus 1, and then du equals 9dx. All right, so if I do that, then this integral becomes the integral of the natural log of u. For now, I'll just leave it dx. So how do I go from here? So if I want to use substitution, I have to finish the substitution, right? So how do I do that? Okay, so dx equals a ninth du. So this is true. It's equal to I can't erase 1/9 times the integral of the natural log of u du. Do we know the integral of natural log of u? No. What's that?
It's like 1. It's like
I mean, if you don't have memorized, I wouldn't be shocked, but there's other ways we can get there. So I think substitution is helpful for making the inner function there be simpler. But what else can we do to just handle the integration of natural log? Integration by parts. So if I set up integration by parts, then I have to identify u and a dv. What should I have? What should I call u and dv?
Use natural log of u.
Why are we choosing u to be natural log?
Maybe
we should probably choose some different letters, huh?
Yeah.
A and db. So if I say a is natural log of u, what's db going to be equal to? Du. Which means the other pieces are, what's b? U, and what's dA? 1 over u du. So following that, this integral should be ab. So u natural log of u minus the integral of u times 1 over u du. And I forgot to carry the knife. Questions so far?
Can you write down the equation real quick?
For integration by parts?
Yeah.
Yeah, so we usually use u's and v's, right? So, but if we were to do this, the integral of, we did adb, it's going to be equal to ab minus the integral of b dA.
You would be V, right? And then DA, DU, like, and then.
Yeah, I mean, so all the A's and DB's and so on that I underlined, those should match the kind of like 2x2 table we set up on the left. All right, so now I have 1/9 times u times the natural log of u minus the integral of just 1, right? So now I get 1/9 of u natural log of u minus u plus c. I messed up with that 1/9, didn't I? Now it looks better. All right, last move. What do I have to do? Yeah, so now undo the original substitution. What was u equal to? So 1/9 times 9x plus 1 times natural log of 9x plus 1 minus 9x plus 1 all plus c. So we did a couple different things there, right? We did integration by substitution to begin, and then the bulk of this was integration by parts. Any questions on this one? All right,
Can you go back?
I think. Yeah. So I'm gonna post these, or I'll at least post the video. I don't know if I can actually like get the PDF, but I'll post the video. What else?
We do one that deals with like the trigonometric functions, so it's like
Yeah.
get five. I don't know one off the top of my head.
Okay, well, I'll try one. So I heard secant to the 5th of x times tangent x. Let me think. I hope that works. I'm almost sure it does. Okay. I reserve the right to go back and modify it in case it doesn't, but I think this works. All right, so how do we start handling this one? Break apart the secant. How come?
It's right in the secant cubed.
Okay.
It's square root of plus.
Okay, so I agree that all of these things are legal and fine to do. But let's also think about if they're going to help us. So tangent squared plus 1, you said? All right. Is that going to help us where we want to go? So we're doing these basically, the Pythagorean identities allow us to basically take any of the trig functions, as long as you have a like any of the trig functions squared and swap it out for something else, right? For basically you can trade it for some other trig function squared. So that's always possible. Go ahead.
I think you better keep it as, secant to the 4th as secant to tangent x.
Why do you think that?
Because then you can say u equals secant x.
Okay, so that's what I was going to start guiding us toward is if we break it down like this, then I agree that it makes the integral easier to do, but like what tipped you off that you should take out one secant like that? Still, this is your idea.
Oh.
Sorry.
Well, I was looking, I knew that I had to either set u equals secant x or tangent x.
Okay.
And since secant has an odd power, it would be difficult to get just a secant squared x on its own to cancel out with the derivative of tangent x, so I went the other way.
Right. So not only difficult, but it can't be done.
Yeah.
So yeah, the Pythagorean identities are useful, but they're pretty limited in that they can only deal with even powers of things. So a couple things to keep in mind here, like this, we did a lot of different kinds of trig substitution integrals. But the ones involving secant and tangent, keep these things in mind. If u equals secant x, then I'm going to have to find the du somewhere, which is what for secant x? Secant x tangent x dx. As opposed to this, if I have u equals tangent x, what's the corresponding du there? Secant squared x. I don't think you're going to be able to get that here, because I started you off with secant to the fifth. So now, I believe this is the one we want. So if I say u is equal to secant x and du is equal to secant x tangent x dx, then what does this integral become? You're the fourth du, right? That we can do. What does that integral become? 1/5 u to the fifth plus c. And then 1/5 of what? Secant to the fifth x plus c. The biggest thing that I think is key for this is recognizing what substitution you want to kind of push toward. I strongly believe there's no way to get to an integral that can be done using u equals tangent x. I'm not going to say there's no other way to do this, but I think what we just did is the most direct. Any more questions here?
So you would recommend when it's like the odd number, like trigonometric function, so there's secant,
Mhm.
to use that as u? If it like works?
I think odd power on secant, that certainly tells me that I can't basically I can't get to an even power of secant, or I can't get to secant squared. But one thing I will caution you on is this, like I believe if I did this, secant to the fifth of x tangent squared of x, I don't actually think there's a way to do that. Because if you let's say you set u equal to secant x, I don't think there's a way to get secant x tangent x to complete that substitution. So, but I think you're cluing in on something important. If you see an odd power of secant, that's probably going to tell you one of two things: either to use secant as your substitution, or that you can't progress. It'd be really dirty if I gave you option 2 on a test. Any more questions on this one? All right. So far, I think we've seen something from the integration by substitution arena. One by parts, and this is the trig substitution. What else we got?
We do also one part, we would have to get like the constants A, B.
Yeah.
Like A, B, and C.
You have a specific one? Yeah. Was that?
That's one complex, like.
Yeah, I'm just worried if I come up off the top of my head, I'm not sure it'll work. It'll always work actually. I don't guarantee the constants we get will be friendly, but yeah, we can do it. So can I throw in all the complications at you?
+1.
What's that?
I got +1. Or minus.
That's a -1 right here. There's probably a way to erase on this whiteboard tool, but I don't know what it is. So it's going to look gross. All right. So actually, that is not. Yes. No. So what is this decomposition gonna look like?
A plus B plus GX plus B.
What, what are the denominators for all those,
Oh,
A over what?
X minus one,
A over X minus one. I agree, that's one of them. What else?
X minus three.
What is the numerator to the X minus one squared bit? We can get away with B, and I'll explain why in a second. And then what else?
CX D over X squared.
CX plus D over X squared plus 4.
Okay, how did you decide to do the CX plus D?
Good question. Why?
The power.
What about the powers? What's that? I have X squared. So right here I have degree 2. So the polynomial in the denominator is degree 2, which means the expression in the numerator has to be degree less than 2.
Okay,
So, but all I can say is that it's less. I can't say that it's a constant.
then why didn't you do that with the?
So here's what's going on with the, so we got two different considerations here. One, this is a repeated factor. And this is a, I'll call it a quadratic factor, but it really could be any higher degree. I'm gonna, let's say we treated this A and B thing the same way, then it would be AX plus B over X minus 1 squared. I don't think that's going to help convince you. Let me substitute that for a simpler but more, but it'll be an easier way for me to convince you of what we're doing. So 9x to the 5th plus 2x over x squared times x squared plus 4. So how do we handle just the x squared part there? What are the factors going to be? X and x squared, right? A over x plus what over x squared? B over x squared plus whatever else. So that x squared, that's a repeated root, right? But I could also treat it like it's a quadratic root. So if I treat it as a quadratic root, then that means I got to look at it like this, right? Ax plus b over x squared. But can I simplify ax plus b over x squared? That becomes ax over x squared plus b over x squared, which is identical. So basically, here's the shortcut that we're sort of making when I just have b over x minus 1 squared. Because I'm already looking at the linear, like the x minus 1 to the first power, in addition to x minus 1 to the second power. Basically, whatever higher order terms might show up in the numerator are going to be covered by the fact that I only have this here. I only have the linear x minus 1 here. So another way to show this is, would you agree that this is legal? I'm going to square this x minus 1 and multiply this by x minus 1. Okay. That's kind of equivalent to, not kind of, that is equivalent to treating it like I did down here. This would simplify very much the same way. That's probably going to be how I explain it from now on, because I'd like that. Any questions? Go ahead.
Not that, but when should or can you do the weird, funky division thing?
That's a good question. Do we do it here? I got a head nod, a couple of head nods for yes. I would do it here. Why? Go ahead.
The numerator is a higher power. than the denominator.
Right, so what's the degree of the numerator? Degree 5, and the denominator? Degree 4. So basically, yeah, before I would even go to this decomposition, I would have to divide first. Okay, I don't want to do this one. I just wanted to talk about like, this is a good one to illustrate like all the different kinds of considerations you have to set up the decomposition, right? Okay, but let me come up with one that's actually like manageable and doable. I don't think the numerator matters at all. Question or go ahead.
Like, on the homework for that chapter, like there were all these like different kinds of, like, he would give us, like, it would like look like this. Like, you know, like,
I'm not necessarily going to give you what the decomposition looks like.
alright, so it would be like, so like, we would know it has to be like A over like X plus B. plus,
Yeah.
like,
So I mean, like this last one we just looked at. Yeah, I would rely on you to decide what the decomposition looks like. So let's talk about. I mean, I think all the consideration or all the like things I've had you look out for showed up here, right? So we had repeated factors, quadratic factors, and then this one would necessitate a long division step as well.
Like there, okay.
Yeah.
What, A, B, C, or D
Mm-hmm.
would you solve first?
So after we cleared the fractions, so this is as far as I want to go with this nasty gross thing. So if I multiply both sides by the denominator, then I would get A times X minus 1, right? Plus B, no. A times X minus 1 times X squared plus 4. Plus B times X squared plus 4. Plus CX plus D times X minus 1 squared. Yeah, it's gonna be nasty. I think I only have one good choice what X value to pick first. 0 would be good, but I think there might even be a better one out there. I think 1's best.
Oh, because it will cancel the C and the D.
And the A.
Oh, you're right.
So yeah, if you start with X, so you have 4 unknowns to solve for. I think you can get B for free to start.
I remember when Kevin got homework, I was really confused because it was like the C and the D had like an X plus a number.
Yeah, so let's revisit. Why does the CX plus D? So yeah, why do I have like that linear numerator, the CX plus D numerator? Whereas in the other ones, I just have constants. What's the difference with that CX plus D term? Yeah, you have your factor there is higher order. It has a degree too. So when I say higher order, I mean higher degree. Those are equivalent terms. As opposed to X minus 1 is a linear factor, degree 1. So the only way for you to be less than degree 1 is degree 0. Degree 0 are no variable, only constant. So that's why I have the A and B for those ones. Go ahead.
How would you go about like solving for C?
I probably would next choose X equals 0. So basically, I think the next, I think you had one in the homework list where you had 4 unknowns. I'm kind of curious what kind of things you did. I think what I would do is, I think the very first time we did this, we just like expanded all the parentheses. And then when you do that, you can match all the coefficients of X cubed on the left side of the equal sign have to equal all the unknown constants that are coefficients of X cubed on the right. So you can set it up that way, or you can really just choose 4 values of X and get 4 different equations and then solve that system with a matrix or Hopefully there's enough, hopefully that it's like sparse enough that you can solve it by hand without too much trouble, but no, when you, 4 unknowns it can get out of control, which is why I think it's fair game for a homework assignment, but probably not for a test. But all the methods and processes and like the way you split up the fractions, the way you decompose, all those things are identical. I just like, this is just like kind of the worst case. So let's actually complete one that's a little more manageable. All right. Or did I go too far the other way? Is this one too simple? Okay, I like this one now.
What the denominator.
I can split the denominator. Yeah, I mean, we can't do a partial fraction thing unless our denominator is factored. So let's start there. How does the denominator factor? The x minus 3x plus 3. Cool. Now what? Go ahead.
Shouldn't we divide first?
Yeah, we can divide first. What tells you I have to divide? Right. Remember, when you divide, I have to hold places of all the powers of x if they don't actually have terms. All right, how does this division work? What's the first term in my quotient going to be? 4x. Now what?
4x plus 36.
Okay, so sounds like you kind of do the subtraction all at once. So I get 36x plus 0x plus 18. Now what? I think that's as far as we can take the division, right? So based on the way the division went, I just traded that integral for what new integral?
Plus 36 plus 18 over x squared.
And I will put the factors back in. All right, let's take a pause right there. Any questions about how we made the 2 steps from the thing I gave you to where we are now?
Long division.
What's that?
Use long division.
Long division to get the quotient of 4x and the remainder of 36 plus 18, 36x. Yeah, there should be an x in there somewhere. 36x plus 18 over our original denominator. Anything else we need to revisit about how we wound up here? If not, then how do we continue?
This is x minus 3 plus 3x plus 3 equals 42x plus 18.
Okay, so now we're going to do partial fractions, but only on the part that actually has fractions in it. So we're going to split this up into this sum. Okay. Then from there, what can I do? What's that? Clear the fractions. If I clear the fractions, what's left?
The x plus 18 equals 8 times x plus 3 plus 3x minus 3.
Okay.
36x.
Yeah, how many times am I going to write that down wrong? Okay. Thank you. Excellent. What do you want to do from here?
Do the value for x.
Choose a value for X. What's a good candidate for? Why did you choose 3? It cancels the B term. So if X equals 3, then I get 36 times 3, which is 108 plus 18, 126. Yeah, this, I don't promise these are going to be nice.
It is,
Oh, is it?
it's 21.
Oh, okay. A is 21. That's useful. What else? X equals what? -3 sounds wise. So that's -108 plus 18. So -90 equals -6B. So B equals 15, right? Okay, so now I think the partial fraction part of this is over. So I'm integrating this function 4x plus 21 over x minus 3 plus 15 over x plus 3 . Can that integral be done? Cool. What is it?
Two x squared.
2x squared.
After y, that's x c. Plus 15, that's after y, that's x c.
Good. Any questions? All right. What else? Go ahead.
When you're doing the trigonometric substitution.
Mhm.
And you have definite intervals,
Yeah.
how do you reset those values?
Yeah, that's a good question because usually, and I saw this on, I haven't finished grading the written homework, but I've graded a few of them, and yeah, that can be a problem. That's good because I don't want to try to cook one of those up. Go ahead.
It's not a nice one. It's the bounds are 8 and 0. And it's x to the 3rd power times the square root of x squared plus 16.
Cool.
Or
Right.
64. I
Yeah.
don't got 16.
Let's not even. I don't want to do that. X cubed times the square root of x squared plus 64.
Yeah.
Cool. All right. So yeah, I think this is a good candidate for a trig substitution. But which one?
And
8 tangent squared or 8 tangent theta. Why'd you choose tangent?
plus 1.
Tangent squared plus 1, but yes. And where'd the 8 come from?
That's a factor. Like it's square root. It's square plus 8 squared.
Yeah, so basically we're gonna have to be able to factor out the correct constant or the right constant to actually get your trig identity. So if we choose x equals 8 tangent theta, then what's dx? 8 secant squared theta. Your specific question was about the bounds, right?
Yeah.
Okay, so the thing to keep in mind here, because I don't know how to work out that way, but for a lot of these, you're given an integral in terms of x. You immediately substitute in terms of theta, and then if you need to, you're going to do a u substitution somewhere, right? So basically the thing you have to pay attention to is what language all your substitutions speak, essentially. So what are these values 8 and 0 in terms of? Those are x's, which means 0 equals 8 tangent theta and 8 equals 8 tangent theta. So I mean, we didn't even go far enough to get to a U substitution for this one, so it's a little less ambiguous as to how the substitution goes, or how that transformation of bounds goes. But yeah, those are X values. And I think the other thing here is that pretty much any other time when we're not, like, any other time we have to transform the bounds and we're not doing a trig substitution, you're basically evaluating what the bounds are, right? You have some formula U, and all you gotta do is plug in X and you get it, right? These you have to solve, you have to go backwards. So that definitely makes this at least unfamiliar. That's the direction you're going. I did see a couple people on the written homework, like whatever the equivalent numbers for the bounds were, they would put like the bounds in for the angle and take like, so right here, it'll be a lot easier for me to explain if we finish this. So basically theta is going to be equal to the inverse tangent of 0/8, right? What I saw a few times on the homework is that basically trying to, like, the equivalent would be trying to take the tangent of 0. I guess that's a bad example because that is 0. But basically make sure, just bottom line, make sure you're plugging in the right values for the variables they actually belong to. Go ahead.
Get around that by substituting everything back into X.
Well, maybe I don't understand what you're asking. I think that's what I'm doing here.
No, like if you go all, so you end up with, for this one, you end up with U. And if you just fill back into U to theta and then back from theta to X.
Yeah, that'll work.
Okay.
Yeah, so what we've typically done when we do integration by substitution with definite integrals is we don't usually come back to what the original like variable was, and that's fine. So basically the bottom line is that the bounds and the function have to be written in the same variable. I don't care it doesn't matter what that variable is, as long as they're consistent. Go ahead.
I had a question with, like, so when you solve this out a little bit, you'll get under the radical, you'll be able to substitute for h secant squared, which would cancel out your dx. And then you're left with just your a tangent theta, and then all that cubed. Could you then substitute back into x? Or is that not allowed?
You can, except it probably wouldn't be as simple as you think. So should we finish this one? I mean, I know this your specific question was about the bounds.
Yeah.
Okay, but I do think it'd be worthwhile if we just kept going. So let's get the bounds. I think the lower one is 0. What is the upper one? Should be the inverse tangent of 1, which is pi/4. So we've done a lot of things here to transform this integral. So the integral from 0 to pi/4. X cubed becomes 512. Is that right? Tangent cube theta times the square root of 64 tangent squared of theta plus 64. 64 times 8 is 512, right? I'm gonna leave it until someone says otherwise. I'm pretty sure that's right. Okay. All right, so now what? If you factor out the 64, at this point, we don't have, I mean, we don't, so even though we have ways to, I mean, we have recipes for the substitution, we don't have to apply any of them. So I think right now it's probably better off to simplify this and see where that ends up.
We can plug it in later, right?
Yeah, I mean, you can always, you can use them at whatever time you want. So if I factor that out, I get tangent squared of x, or tangent squared of theta plus 1, which is what? Secant. So that was the whole reason we did the x we did. So this becomes 8 times secant theta. Five twelve times 8 is 2048. Times tangent cubed theta secant theta d theta. So Colin, was this where you're asking if you could drop the x back in?
Yeah, well, I guess I incorrectly simplified that, so I had the secant squared cancel out.
Oh, okay.
Which wouldn't work.
Delta theta? Oh, when you substituted the,
Is there-
secant, yeah. When you substituted delta theta. for-
Oh, no, because I didn't substitute in the. Yeah, I didn't do that at all. So let's clumsily tack it onto all my previous steps. So dx is equal to. Yeah, that's bad. So dx is equal to, or sorry, d theta is equal to dx over 8 secant squared, right? Thank you for the catch. All right, so if that happens here. Then this secant cancels with 1 power this secant.
Yeah, why are you? Isn't it delta x, isn't it just 8 secant squared times delta theta?
Yeah, I'm sorry. I went the wrong way and then I plugged in the wrong thing. So all my long speech about you all paying attention to what variable is what, I totally violated it. Okay, so all of that needs to go. Okay, I'm just gonna correct the last step. I hope that doesn't offend anybody. So this, I'm just missing an 8 secant squared theta, right?
Yeah.
Okay. All right. Sorry about that. Are we happier with it now? Except for the fact that I can't multiply. Okay, so now 4096 times 8 is, help me out.
32,768.
So 32,768 times tangent cubed of theta, secant cubed of theta, d theta. All right. Now, you want to take that out of the integral? Really? You don't want to just keep thinking about that? Do I have any idea how to deal with integrals like this? Heard some wise words earlier about if we have odd powers to a secant, we do something specific. Will that work here? I'm not going to say no, I'll say not yet. I think that will work, but I think there's something that has to be done beforehand. Go ahead.
Separate tangent cube theta into tangent squared,
Okay.
and then convert tangent squared to secant squared minus 1.
Okay. Because I'm concerned about room, I'm going to do that all at once. So I'll factor out one of these tangents. I'll let the other one become, you said secant squared minus 1, right? Okay. Now what? U equals secant theta? Is that gonna work?
Because then it's derivative of secant, it's the tangent, that's what.
Okay, so let's reserve a secant for that purpose. So this becomes secant squared theta minus 1 times secant squared theta times secant theta tangent theta d theta, right? Does it make sense why I rearranged the things that I did? So we believe that we were doing all of this to set up a u equals secant theta substitution. We know that du is equal to secant theta tangent theta. So now let's use those 32,768 times the integral from 0 to pi over 4 of what?
And then u squared plus 1.
Minus 1 times u squared times du. That's a lot nicer looking, right? No, we did that. Oh no, you're right. They gotta change again. Or do they?
If you want to substitute that.
I mean, we could integrate and then just go back. What do you want to do? Okay, cool. Would you be offended if I did this? Keep asking if you'd be offended, like I'm really worried that I'm really out of line. So u to the 4th minus u squared, right? That equals this. I'll make sure I say this is equal to. No, my bounds were not u bounds, were they? They're theta bounds. That's not even what I meant to do. I don't need to write that down again. I know how to integrate this. So this becomes 1/5 u to the 5th minus 1/3 u cubed. Then I'm going to evaluate this at theta equals pi over 4 and theta equals 0. So you said you did not want to transform the bounds. You wanted to retransform or just take the function back to thetas. So 32,768 times 1/5. What was u? 1/5 secant to the 5th of theta minus 1/3 secant to the 3rd of theta. Now I don't need to call these theta anymore because everything's theta. Ooh. What's the secant of 0? What does secant even mean? 1 over cosine. What's 1 over cosine of 0? Oh, thankfully. So when I plug in 0, all those are going to become 1, right? What is the secant of pi over 4? Root 2. We agree with that? Cosine of pi over 4 is 1 over radical 2. Should we just be completionists and get this big stupid number? 1/5 times, we said root 2, right? So 1/5 times 2 to the 5 halves power minus 1/3 times 2 to the 3 halves power minus 1/5 minus 1/3.
Can we expect to do this?
I mean, I'm gonna say no. I mean, I took How long did it take us? Like, we spent like the last 15 minutes on that. The concept, the process, the technique, absolutely. This thing got a little out of control. But
On the test, how far are you gonna be able to go? Expected to simplify.
I'll specify if I really have some standard I want you to go to. That's fine for me. I'm not going to pretend to look simple, but that's a number. That's an answer. If I asked for it exactly, I would stop there. Cool. All right. I got 55. I will post the video and I'll try to figure out how to. Oh, is that what this button does? Yes. Cool. I'll post the video. If you just want to look at the work we did, I'll post that too.